Welcome to Chemistry Podcast 4.9. This is oxidation reduction reactions, and this one is going to twist your brain a little bit because we've got to get a couple concepts down before we can even get to balancing what's known as a redox reaction, and they're kind of fun in a chemistry sort of way. So let's look at this. There's a few things that we need to think about where last year we just worried about balancing equations and we only worried about 5 different types: single replacement, double replacement, synthesis, decomposition, and combustion. Well, this is a new type of reaction, and what happens often in chemical reactions is that electrons get transferred. Oops, let me get my pen going here. Electrons get transferred, and so one of the ways to balance these is to kind of keep track of the electrons. We produce a certain number of electrons in a reactant, and we want to figure out how many electrons were produced and I guess you could say absorbed by the products. But this is going to take a little bit of time, and we will look at how we start. So let's look at what's known as oxidation states. Now, the nice thing about oxidation states is it's very similar to charges. Okay, very similar to charges. I guess I should say ionic charges. All right, and in fact, we might defer to the ionic charge quite often. But what this really allows us to do is kind of keep track of these electrons as they're being transferred in this reaction. And it doesn't really occur this way in nature. For example, we'll say chlorine has an oxidation state of 5. Well, that doesn't really mean it lost or gained 5 electrons. But for us, it's going to allow us to really focus on how many electrons are being transferred. Now, again, we're dealing with a memorization thing. I've got a bunch of rules here, and you'll find that they're pretty easy to memorize. You may need to make flashcards, but it might be something that is not too bad. So let's go through these and just kind of see how they are. All right, here's the first one. The oxidation state of elements in their standard state is 0. So let's say, for example, I was mixing zinc with oxygen, and we made good old zinc oxide. Okay? Well, in their standard state, it's at room temperature, 1 atmosphere, zinc is a solid, all right, and oxygen's a gas, and it's always O2. So if I were to ask you to assign oxidation states, you would say this is 0, oops, and this is also 0. All right, so oxidation states for elements in their standard state, and that's just, what you'll find them in nature, that is 0. Oxidation for monatomic ions are the same as their charge. So, for example, let's say I had a sodium ion plus a chloride ion, and I made some table salt. All right. Well, the oxidation state of this thing is +1. The oxidation state of this one is -1. Right? And so that's a pretty easy rule so far. So you've got 0 if they're in their standard state, the same as their charge if they are an ion. So let's look at the next one. Number 3, oxygen is assigned the oxidation state of -2 in covalent compounds except as a peroxide. Now, what's nice about this rule is if you think about it, if you think about oxygen as an ion, what was its charge all the time? -2. So that's not something new you really need to memorize. And as a peroxide, we already know this, H2O2, the oxidation state of oxygen there would be -1. All right? So that's the only exception. And you don't see very many peroxides. You see sodium hydroxide, peroxide, and hydrogen peroxide. Those are the 2 that we see most often. All right, in compounds with nonmetals, hydrogen is assigned an oxidation state of +1. Well, that's good news, right? Because as we memorized last year, hydrogen almost always forms a +1 charge, right? So its oxidation state is always -1. Now, when would it be a -1? Well, if you had a metal hydride, something like this, sodium hydride. All right, then hydrogen would have a charge of -1. So again, these are things that we already know from good old ionic charges, so we're not having to memorize anything new. In its compounds, fluorine is always -1. Now, fluorine is the most electronegative element. It is the king, and no matter what compound it is, it gets an oxidation state of -1. Now, by knowing these 3 oxidation states, you can figure out virtually every other oxidation state of other elements, and so it makes it really easy. Just remember those three mostly, and we'll go from there. Now, here's the important thing. But again, this is almost a review. The sum of the oxidation states has to be 0 in compounds or equal the charge of an ion. So, again, if we're talking about an element, if we're talking about a compound, the oxidation state has to be 0, just like in an ionic compound. So, for example, the oxidation state of all these has to equal 0. And does that? Oh, sure it does. Oxidation state of +1, oxidation state of -1. Now, this charge of the ion, let's imagine it's a polyatomic ion. Oops. NO2 minus, right? Let's say it was a minus there. Well, oxygen's always what? Oxygen's always a -2. And since we have 2 of them, I have a total of -4. All right, and then nitrogen, what's it got to be? You can think of algebra. X plus -4 equals -1, right? Just like right there. And so nitrogen's oxidation state must be 3. All right. So let's put a couple of let's put a couple compounds up there and see if we can figure it out. Assign the oxidation state to each element in the following. Well, oxygen is -2. Oops, get my pen going. Okay, so oxygen is -2. Now think about this. If oxygen's -2 and we have 2 of them, that gives us a total of -4. What plus -4 equals 0? So carbon in that situation has to equal 4, right? Nitrate. All right, let's try nitrate. Let me erase here and get a little bit of room. Okay. Nitrate has to be, or oxygen again, the O here is -2. Okay, there's -2 there. There's a total of 3 of them, so that's -6. So what plus -6 equals -1? And in this case equals 5. Right? What I'd like you to do right now is pause the video and write the oxidation states for the rest of the 3, and then I'll let you check my answers. All right, look at my answers here, and hopefully they'll match yours. The challenging one here would be, did you get the oxidation state for sulfur at +6? Did you get the oxidation state of iron here at +3? Right? And then look at this one. This is really unique because this just kind of proves that this is a man-made thing. This is so we can understand what's going on. An oxidation state of 2 2/3. Now, I'll be honest with you. I never see any of this in a normal AP class. You don't come up with an oxidation state like that. But I just threw it in there to let you know that this is something for us to keep track of charges, and it really doesn't pertain to, you don't have to worry too much about something like this. This is just kind of a unique thing, all right? But I threw that in there. So if you got that, great. If you didn't, don't worry. We're going to practice it in class so that you can get good at it. Let's do another one. Pause the video, write these out, see how you do, and then we'll go on to the next thing. All right, how'd you do? Look at those. Hopefully you've got the right oxidation state for nitrogen. Let's see, where might there be a problem? Might be a problem right in here somewhere. Oops, let's see, right there. Okay, did you get this one? Okay, I can see that being a problem because sometimes students forget that this is the standard state all by itself, so they always have a charge of 0. So again, take a note, do a star, jot something down to let you know that you need to ask me about this tomorrow if you got stuck on them, and we'll review it, and hopefully there aren't too many questions, and I'll see you next time.